Okay, let's get going. So we are here at Wednesday the 25th. Today we are going to talk about, we're going to do a little thing on Unix tip of the day. I've actually showed you time before, but I'm going to just show it to you again. And then we're going to talk about some homework 3 clarifications. I apologize, there were some mistakes in the code itself for the homework 3 and mistakes in the in some of the comments for homework 3, but they're very minor and they're very easily fixed. And so if you've been working on the code and you've got some issues with, hey, this doesn't work, look on Piazza. We've kind of handled it on Piazza, and I've updated the code. So if you actually haven't started it yet or downloaded it, you don't even need to worry about the things that have come up so far. Wouldn't surprise me if something else comes up in a little bit. But we're going to talk a little bit more about homework 3 clarifications. Then we're going to do a little bit of a math review. Because the next little kind of set of things that we're going to do is we're going to actually start digging into some of these algorithms we've been talking about and figuring out details about how they run and how fast they run in what we call an asymptotic situation. Whereas as you get inputs that are bigger and bigger and bigger, how does the program behave? And we're going to have to get a little bit mathy in here. Not too bad, actually. But if you happen to be good at math, you'll probably like some of the stuff. I've got one slide on here, which if you're not a big math person, just shield your eyes a little bit, because it's a little ugly. But it's not too bad. And then we're going to, so then we're going to go into this asymptotic notation, and otherwise known as big O notation. In Comp 11, did you ever hear the word big O or talk about it? OK, that's probably good, because it probably would have been a little bit too much for just learning to program. How about Comp 50? Those of you who took Comp 50. Anybody in here Comp 50? No? You didn't do the? OK. All right. So, well, anyway, we'll get to all that. So before I start, any questions? Anybody have anything so far? How's the homework 3 going? Hope it's going all right for those of you who started it. By the way, there may have been some concerns about homework 3 being, hey, this is like tricky stuff. We have to really, I don't understand what I'm expected out of this, right? If you don't understand it, well, that's kind of by design in the sense that you have to actually think about it, right? I'm not going to just say, in the design documents, you hope it's laid out clearly. But if it's not clear to you, that means you actually have to dig in and go, OK, what would it mean to say, find the next time in a schedule, right? And it says that in the document. But to actually figure out, OK, what do I have to do to find the next time? Well, I have to look at all the times during the day, at least starting from when I want to schedule some event, right? And I have to look at the other events that are in there, do some comparisons, and then if it doesn't fit, like the event over or conflicts with something, then you have to go and say, all right, I need to have this event that I'm trying to schedule later in the day. Well, what's later mean? After the event you just checked, et cetera, et cetera. So those kind of thinking things are kind of by design to force you to think about how to do something and then code it up. OK? Let's see. So most of the fixes, like I said, most of the fixes were very minor online, a couple little mistakes. But they should not hinder you if you look on Piazza and make the changes if you've already done that. One thing that did concern some people was, hey, it looks like the events that are early in the morning get scheduled, or somehow later in the day get scheduled earlier, even if there's no conflicts or whatever. If you do decide to look at some of the input files that I've given you, they are from a Google Calendar export. OK, well, they're actually toned down from that. They're as if you got it from Google Calendar without a lot of extra junk in there. And the way Google Calendar does it is they have these times in GMT. I mentioned this yesterday, not our time zone. And so the import function, I've already written all that for you. It imports them and changes the time to an actual Eastern Standard Time. So if you were running this in California, well, sorry, it's going to be the wrong time for your Google Calendar, because I just said just convert everything to Eastern Standard Time. It was a little easier than doing it some other way. OK? And so you don't have to worry about that. But that's why you might see the times not quite lining up from the import functions. If you put your own times in, they will be in Eastern Standard Time, and everything will work appropriately. Make sense? OK. All right. Any other questions or concerns about homework 3 so far? Anybody have any, like, I don't get this, I don't understand what I'm being asked, it's too hard, etc.? It's too easy? Anybody finish it yet? You don't have to raise your hand. Like you fast people. All right. So that's about all I have to say about that. We do have lots of office hours, and we do have lots of time over the next few days to meet. So feel free to email me if you want to meet individually. I've also got office hours today and tomorrow in the afternoons, I think. Yeah. Nothing else? OK. Let's go into a little bit of math review. Okay. This is actually not so bad, and I doubt most of you or any of you have actually taken the math class that computer scientists actually take called discrete mathematics yet. You probably have not taken that. But hopefully, in some point in your life, you have seen the summation symbol here, right? And you have seen how this actually goes ahead. A couple of you have taken or are taking it, discrete math now. I know that. Anyway, this is what this means, right? If you have a function I, and you go from a to b, this just means add up the integers in this case from a to b, right? It's going to say, or the functions rather, if you've got some function, the first thing you're going to add is the function of a, and then it's going to be a plus 1, then a plus 2, all the way up to b. Okay, not rocket science here, but that's just what this means. The reason we use this one a lot is because this actually is what loops are doing, right? If you've got a loop and you're incrementing an index 1 by 1 by 1 by 1 by 1, right, you're going to be doing these kind of calculations. And you're not necessarily going to be summing up in the loop. But what you are going to be doing is you're going to be doing something and then doing something to the value plus 1, et cetera. And if we want to count the number of operations that takes, this is how you're going to have to do it. Okay? So, or the stuff that's inside that function. You've got to count that amount of time. OK, so that's summation. Fairly straightforward. Okay? We also have geometric summations, which are saying the following. If you are doing just some integer a, okay, and a happens to not be 1 in this case, because you'd end up with not a good solution at the end here. If a is not equal to 1, and some integer n, which is positive, or 0. Okay, if you do the summation of 1 plus a squared plus a to the n, basically, when you sum all that up, this is what you actually get. 1 minus a to the n plus 1 over 1 minus a. Okay. If you sum all the way up to infinity, instead of just stopping at some value, you're going to end up with, this is actually going to compress down into the following. The summation from 0 to infinity of a number raised to the ith power from 0 to infinity equals 1 over 1 minus a. If a is less than 1, I should say. If it's not less than 1, it's going to be unbounded, right? But if it's less than 1, it's going to be 1 divided by 1 minus a. All right? OK. And what I realized after I wrote this was we're probably not going to get into some of this stuff later or today, but we're going to see it anyway now and do a little review. OK. So if you are a computer scientist, these geometric summations actually become really, really important in the following sense. Okay? If you are doing 2 raised to a power, okay? If you're doing 2 raised to a power and you're summing up from 0 to some n minus 1 in this case, okay? What you've got is 1 plus 2 plus 4 plus 8 plus da 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 plus 2 to the n minus 1. And what does that actually equal? That equals 1 minus 2 to the n minus 1 over 1 minus 2. And if you do that out, okay, you end up getting 2 to the n minus 1, which is the largest integer that can be represented in binary notation using n number of bits. What does that mean? Using n number of bits. If I have 3 bits, right, what's the maximum integer I can represent with 3 bits? 7, right? You can do 0, 1, 2, 3, 4, 5, 6, and 7, right? And if you turn this into binary notation, right, 0 in binary is what? 0. Then 1 in binary is 0, 1. 2 is 1, 0. 3 is 1, 1. 4, now we've got to have 3 bits. And has everybody counted in binary before? No, you haven't counted in binary. OK, let's go back one step. All right. I haven't really prepared this, but if you're counting in decimal notation, okay, you count up until, and you're just counting up, right? The whole point of decimal notation is that there are 10 different digits, right? 0 through 9, 10 different digits. And if you're counting up from 0 to whatever, you count up and you get one particular digit until you get to 10, and at that case, you've got to use 2 digits. Well, it's the same thing in binary. Okay, if you're counting in binary, you've got how many digits? 2, right? So in order to count up in binary, you can count 1 just fine, or 0 just fine with 1 digit. You can count 1 just fine with 1 digit. Okay? But now, how do you get 2? Well, it's exactly like going up to 10. You've got to use 2 digits now, and here's how it works, right? It goes 0, 1, and then it's just like counting from 9 to 10. You put a 1, and then you start over from the beginning of the character, or the symbols that you have, right? 1, 0. So this is 1, 0. This is 1. This is going to be 2 in decimal because you've had to go up and you've had to add one more place, binary place in this case. Okay? And then 3. Okay, well, what do you do when you go from 10 to 11? You add 1. So 3 is going to be 1, 0 plus 1 extra, 1, 1. Okay? 4. Can we do 4 with 2 digits now? This is exactly like getting to like 21 in the sense that you've gotten up to the, or sorry, no, I lied, 99 in the sense that you're getting to the one where you have to use one more digit. So 4 is going to be 1, 0, 0. And then 5, you can start counting again, 1, 0, 1. And then 6 is going to be 1, 1, 0. And 7 is going to be 1, 1, 1. And then you'd have to go to another bit. So how many bits did we use to get all the way up to 7? We used 3, starting at 0, by the way. Okay? So that's where this comes from. And if you don't get how to count binary, it's not the biggest deal right now. But you can ask in office hours or go look it up online. It's pretty, it's relatively straightforward. I used to have an actual watch that counted in binary, but it broke, so it was too bad. Anyway, so if you look at this formula here, if you're counting from 2 to the I, if you're going all the way up to n minus 1, n is the number of bits you need to represent the number of, the largest integer that you can represent using n number of bits. Okay, so if we had one more bit, we could actually represent all the way up to 15, right? Because that's going to be, if you added that up, it's going to be 2 to the 4, which is 16 minus 1. Okay, questions on that? This isn't going to get, I mean, you're not going to have to worry about the binary counting at this point. All right. Okay. So here's another one, right? If we were to just add up all the integers, now this is one that, there's this story about this, probably apocryphal, about Carl Gauss, one of the famous mathematicians. He was in his grade school class, and his teacher was trying to keep the kids busy, as teachers do, right? And she said, I want you all to add up the numbers from 1 to 100, right? And next thing you know, Carl Gauss has his hand up in like 2 seconds and says the answer, right? What is it? 5,050? Is that what it is? No. What's that? Yeah, 5,050. Right. So he says that, and he just spits it out. And she goes, how'd you do that? And well, it turns out that he probably used something like this. He said basically, if you're gonna add the numbers from 1 all the way up to 100, right? Well, let's look at 99, right? If you look at 1 and 99, they add to 100. And 2 and 98 adds up to 100. And 3 and 97 adds up to 100, right? And he basically went through this kind of thing in his head. It's all apocryphal, of course. But he went through this thing in his head, and he came up with this formula and says, this is how you're going to actually do the formula if you add up the numbers from 1 to n. It's going to be n times n plus 1 divided by 2. OK? Straightforward? Oh, OK. Algebra, right? All right. So the other thing that comes up in computer science a lot is this idea of logarithms. Now, I've mentioned logarithms a lot. In fact, we mention logarithms when we talk about the binary search tree and how the height of a binary search tree on average is log n, right? The number of nodes in there. Logs come up in computer science a lot, and logs actually are very much our friend because logarithms grow slowly. And when you have some algorithm or data structure that's based on the number of elements that like changes its behavior based on the number of elements, increases, if that function happens to be a logarithmic function, you can add lots and lots and lots of elements before the function ends up taking too long to actually go, because logs grow slowly. Okay? There are other functions we don't want to talk about, namely exponential functions, which grow very, very, very fast, and you don't want to do that. In computer science, if we say log of a number, if we don't put the little base b here, right, what we mean is base 2. Why? It goes back to this binary thing. We're going to count from zeros and ones, and so our logarithms are, in general, going to be based on log base 2. And so we're going to, if I say something's on the order of log blah, 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 I generally mean base 2. OK, so a log of 1024 in base 2 is 10, because what? 2 to the 10th is 1024. OK? Make sense to everybody? All right. Logarithms, there's lots of different properties of logarithms that obviously you know about from taking math classes before. But doing some of the conversions, when we get a little bit later in the class, you'll see that you need to use some of those. And it's not that hard. It's just you got to remember what they all mean. OK, so that's actually it for the math review. That was it. I just wanted to show you those things in case we talk about logs and we talk about summations and things. And you got to kind of keep that in the back of your head. OK, so let's go into some algorithm analysis. OK, we've been kind of waiting for this for a while. And let's go into it and talk about how we might go about doing some analysis. And what do I mean by analysis? I basically mean, how is this program going to behave as you add more elements to it, in the sense of, if n is the number of elements you input, if it's an array, it has n number of elements. If it's a tree, it has n number of elements. We talk about that many, many times. Okay? And the question is, how do we analyze programs like this program, which happens to be the maximum number of an array, this program? Okay? So let's just look at this algorithm before, so we can just kind of get an idea of what it's doing. We are inputting an array, or we're taking an array, and some number that is actually in this case, it's because of the way I do this, it's actually the length of the array. Okay? There's other ways to do this without it. In other languages, it would be easier. You wouldn't need to pass this in. But I'm just passing in the length of the array and the array itself. And I'm just saying, all right, we're trying to find the maximum. The current maximum, well, it could be the first value. So I'm going to set the first value equal to the current max equals the first value in the array. Then I'm going to say, all right, let's go through the entire rest of the array, starting from 1, all the way up to the end, and check and see if the current max is less than what's in the array. I'm going to now set the current max equal to what that array points to, and that value at that index. Okay? We go through the whole array, and we get that done, and we return current max. Okay, everybody get what the algorithm's doing? This one's not too bad, I think. Okay? How might we go about analyzing this? What are some strategies we might use to say, how is this going to behave as we add more elements? Any ideas? Like, what's an idea? Yeah, go ahead. Mark.
You're basing it off the length of the array, which is where n is.
OK. Yeah, so you're saying, like, ignore things that aren't n in this case. Yeah, that's not a bad idea to say, hey, in this thing, see how n behaves by itself. Like, forget about all that other extraneous stuff. I like that. OK, I like that idea. What are some other ideas? What's an idea if we really wanted to know how this algorithm behaves as we go? I mean, I want to know down to like the absolute last little bit of detail how this algorithm behaves. Then we can't just ignore n, or ignore everything that's not based on n, right? But what would we have to do? Like, how would a computer like go through this calculation, go through this, and like how much time would it take? Can we break this up into little smaller time slots? Is the question. Yeah. Oh, yeah, OK. So we can say, we're going to go through this loop. Are we actually going to go through loop n times?
No.
We're going to do n minus 1 times, yeah. right? Because we actually kind of set the first one to begin with. We could do it some other way where we have current max being like the lowest possible answer first and then go through the whole loop. But this actually saves you one loop, and you know it's going to at least be, it could be the first one. But yeah, you can do that. So you might have to sum all this up and then do that. What about, does it take any time to do this first line here? It does take some time, right? Might be a fairly small amount of time. In fact, it takes 2 operations to do that, right? There are 2 things that happen in this thing. What are those 2 things that happen? Yeah? Dereferencing the array. That takes some time, actually. Yeah, that takes, depending on where in memory that array is, that can take a lot of time, believe it or not. Yeah, so in fact, if the array happened to be somehow you didn't have much memory in your computer and that array happened to be on a disk, right? It could take lots of time. There's a, I was telling somebody this the other day. Once you get into disk behavior versus memory behavior, like all bets are off for a lot of this stuff. Okay, here's the analogy that's generally used. And there's a whole bunch of tiers of memory. We've talked about this before. It's kind of a little side topic here. So there's a whole bunch of tiers of memory. Okay, at the very fastest memory, you've got these things that are called registers. What that is that's like in the hardware, there's certain places in the hardware which store memory, and they are really, 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 really fast. Okay, and you've only got so many registers. In fact, some computers only have like 32 registers or 16 registers, right? But they're super duper fast. Okay, then you've got this memory we talked about before called cache, and you might have 2 or 3 different levels of C-A-C-H-E. You might have a whole bunch of different levels of cache, and that's very fast, but not quite as fast as registers. Why don't you make cache out of registers? Too expensive, not enough space on your computer chip die and all that kind of stuff. You got cache. Then you've got your main memory, right? And that's the memory that's fast, but not as fast as cache. Again, it's too expensive. And then finally, there's other levels. There might be more caches and other kind of things. But then finally, you might have like disk memory. Or even worse, you've got like network memory, like things like in the cloud or whatever, right? Well, here's the analogy that's used. If you're sitting at your desk, and you want to grab a pencil off your desk, and you want to write with it, right? If you're doing a register, that's like the situation. You grab the pencil off your desk, you start writing with it. Okay? If you're in cache memory, it's kind of like the pencil is like on the other side of the room. And you have to kind of get up, and you go over to the other side of the room, and you grab the pencil, and you come back, and you write with it. Right? That's how long it takes. If you're in main memory, it's like the pencil is like kind of a short like walk away from your house, right? So you actually have to go out. You have to put your coat on. You have to go down. You have to walk outside. You have to make sure the dog's tied up. Whatever. You have to walk down the street. You have to grab the pencil that's down the street at your neighbor's house or something. You walk all the way back, and then you start writing with it. Like that's how much time it takes. Okay. Any idea how long it takes to do disk writes or reads rather? On that same analogy. Any ideas? You have to what? You have to buy a pencil. Yeah, you have to like walk down to the store and buy a pencil and get that right. Close. Well, on the right idea, right? Depends how long it takes you to go. It really depends if it's like midnight and you want to buy a pencil before like 2 days from now, right? What the analogy is, it's not that your pencil is anywhere nearby. It's like that you have to get in your car, drive to California, pick up a pencil, and drive back here. Right? Like that's how long it takes to do disk reads versus main memory reads. Okay, it's so much longer that a lot of this analysis doesn't actually work. But going back to the actual point, yes, you have to dereference that array, right? You have to dereference that array here. Depending on where it is, that can take some time. But we're going to just say that it takes 1 unit of time, let's say. Okay, what's the second thing that happens? Yeah, once you get the memory from the array, then you have to put it in this current max. So it actually takes 2 things to do that little guy right there. Okay, my thing's dying. All my laser pointers are dying. So anyway, so we can do that. Now, if you really want to get into the weeds here, like of the actual operations, we can do the following. Okay, we could say, let's code this up in C++, which I just did. Okay. then we can actually, for every line in the compiled program, then we can go and say, what is that doing? It's doing, like, for instance, that max equals the array dereference. Well, at the assembly language like situation, in other words, what the compiler turns that into so that your machine can read, we can go and do that and get each instruction of the compiled program and then figure out how that works. Then we can determine the number of times each instruction is actually done, like in the loops and things. We have to do some math there. And then finally, we sum everything all up. OK, if we wanted to do that, let me show you what it might look like. This, what I'm about to show you, is let's see if I can find it here. It is, there it is. Oh my gosh. All right, this is the output. Now, this was purposely made to scare you. This is the output of your, I did this with the debugging, like everything on and everything. So this is the output of your file in assembly language, right? So when you write your C++, you guys get all frustrated with C++ syntax. And you're like, oh, I hate this language, and it's so hard, and there's so much to remember. Try doing stuff in assembly language, right? Actually, believe it or not, assembly language has like fewer things to do, but you have to do everything yourself, right? You have to like do a loop like it's ridiculous. It's fun, but I mean ridiculous, right? Fun in kind of a masochistic kind of way, for what it's worth. But anyway, so we can go down here. We can say, oh man, where is the program we say? It actually is nice enough to say, hey, this is your line 13 in your original CPP program, right? And then you'd go, OK, let's see what's going on here. We're pushing some values. Hey, look at this. Assembly language has a push, right? I kind of mentioned that the other day. Assembly language has pushes and things. OK, we're pushing it. And what you would have to do is you would have to go through and look at this. And you would have to say, all right, I want to know each little what's going on in each little part of my program. Let's see. I'm moving some stuff. Remember I said you have to do everything yourself? This is like saying, OK, on the stack, we're going to have to put a variable. Well, where do you put it? You put it, a variable is 8 bits long, so takes 8 bytes to write, or whatever it is, and you have to move the values. And we don't want to do this. OK, let me just say we don't want to have to do this for every program that we want to analyze. OK, not that I had to tell you that. But instead of trying to be that pedantic about this stuff, OK, instead of being that pedantic, which is just annoying, it's complicated, and even if you tried to do this, if your computer is your computer has like multitasking capabilities, and the compiler sometimes like optimizes things. I mean, there's lots going on that you don't want to have to dig down into and figure out. Okay, we don't want to read assembly language. We don't want to like dig down under the covers. So we're going to step back. And we're going to do this from a much more holistic point of view. We're doing this analysis. Okay, a much more holistic point of view. What we're going to do is we're going to say, kind of like what we said earlier, what's the program doing at this step in a big picture situation, right? We're going to come up with these things called primitive operations, okay, for our code. And the primitive operations are these ones. And when we find that primitive operation, and we say that the computer has to do that primitive operation, we're going to count it as 1. Right? We're going to say that takes 1 amount of time. Whatever amount of time is, that takes 1. So if you're a really fast computer, that amount of time is going to be much less than if you're on a really slow computer. But it's not really going to matter, because we're kind of looking at the holistic point of view here. So what do we have? What kinds of operations do we have? We've got assigning a value to a variable, right? We've got calling a function. Calling a function now, OK, calling a function takes much more time than assigning to a variable. But we're not going to worry about that for right now. OK? Why does it take much more time? Because you've got to store the stack, and you've got to do this and that. We're just not going to worry about that. OK? It's all kind of hand-wavy in some sense. OK? Arithmetic is going to take some amount of time. Okay? And we're going to say that that takes 1 anytime you do an arithmetic. Now, if you're going to add versus multiply, guess what? It takes longer to multiply in general, although the computer designers these days have made it a lot easier to multiply in the sense that they built it in at such a low level that it's very, very fast. It still takes less time than it does to add, but it's still it takes more time than it does to add. They do it. Comparing two numbers is a primitive operation. Indexing into an array is a primitive operation. Returning from a function is a primitive operation. Okay? You do not need to memorize this list. Okay, I see lots of people writing it down. You don't need to write it down. You just need to. We just need it. We're just kind of getting to the picture here. I'm kind of painting you the broad scale picture before at the end you'll see why we're doing this. Okay, questions on this so far? We're getting a program. We're looking at the operations and we're saying at the bigger picture, what's each operation doing, and how many steps does that take at the base level? Okay. All right. Let's take a look at this again. Okay, this is our array max. Okay, using those primitive operations, we already talked about this one. Okay, this one takes 2 operations to do. Why is it 2? Because you're grabbing the array value and then setting current max equal to that array value. 2. Okay, in the loop here, how much is going on in a loop? I mean, right in this line, there's like a ton of stuff going on. There's a reason that the people who designed C designed loops like this, because they shove a lot of stuff into one line, right? You could redo this as a while loop if you wanted to, but they've like made it much easier. In the big picture, they've said, let's make it easier, and but there's a lot going on here. Okay, there's an operation to set I equal to 1, actually create I, then set I equal to 1. Okay, there's an operation that compares a number, compares I to n, and there's an operation that actually increases the value of I. They don't all happen right at the beginning, but let's see. I equals 1, that takes 1 operation, we're going to say. Even though you do have to create it. That would probably take 2 if you really wanted to get down and do it, but we're going to just leave it at 1 now. I is less than n is a comparison. And how many times does that happen? Well, in a loop, if you're going from 0 to, well, in this case, if you're going 1 to n, you actually do that comparison n times. The last one is when you bump out of there. Okay? And then the same thing with I++, except now you only do that n minus 1 times. But we're going to call that 2 operations. Even though it's the smallest thing you can write in C, basically, or C++, we're going to call that 2 operations. Why? Because you've got to add some value, and then you've got to set it equal to the variable I. That's really 2 things. Yes?
If you're starting with n equals or I equals 1,
Yeah.
would you only compare
Wouldn't you compare n minus 1 times if you're starting at n? Let's think about it this way. The last thing you do before you exit out of the loop is one more comparison. Why do you have to do a last comparison? You have to do a last comparison because you need to make sure that you need to do that check to see if it's going to jump out of the loop, right? So actually, if you go 0 to n, you do n plus 1 comparisons. So this way, we're really doing n total comparisons. Make sense? Sense? OK. I think I got that right. All right. So anyway, and then so the I++ here, that always happens n minus 1 times, but there's 2 operations, so that's 2 times n minus 1 operations. Whew. OK. Let's go into the loop here. Inside the loop, we do this little check, and we do another comparison, right? And we have to do a comparison with the less than sign, and then we also have to do this, dereference the value from the array. That's 2 operations. How many times do we do that? We do it n minus 1 times. This is where the n minus 1 comes in, where we actually do this part inside n minus 1 times. Okay? And so that's 2n operations. No problem. Now it gets a little fuzzy. How many times do you do this one? Right? This one, all of a sudden, it's not so simple. Because what happens is sometimes you don't have to do this one, right? If the comparison up here is such that that current max is not less than a, it's greater than or equal to a, you don't even get to this line, and you skip it. All right, so you have to kind of think about that. Well, can we figure out the maximum number of times this happens? Sure we can, right? We can say, let's say that we ordered the elements from 0 all the way to n in the array, and we had to check every single one, and every time we checked, it was less than the current maximum was less than the value, so we had to make this comparison, or we had to make this setting here. This is 2 operations again. We're dereferencing it again, and then we're setting it equal to current max. So at most, we're going to do this n minus 1 times. So that means we're going to do 2 operations times n minus 1 times. Whew. I'm seeing some faces like, oh, I don't like this. Don't stress about it. Yes?
For the if statement, why is it
For that we sorry, where right here instead of what?
Below that for the if statement.
For oh here. Okay, how many times are you going to go through this now? You're starting at 1 and you're going all the way up to n minus 1.
I understand that it's n minus 1 times.
Yeah.
You said it's 2.
2n. Oh, well, look what happens in here. You've got two things going on. You've got a comparison, and you've also got to dereference this. In other words, you've got to go to memory and grab this value. That takes two things. Sorry?
Why is it not n minus 1?
Oh, why isn't it n minus 1? Oh, sorry, you're right. Sorry, there's two. You're right, it should be. I'm sorry, I was reading it wrong. Yes, you're right, it is 2n minus 1. Thank you. OK, all right, so that's that. Now, is there anything else that this function does that's going to take some time? Return, that takes 1. OK, well, this is the final value, and then the return takes 1 operation there. OK, all right, so the loop total here is going to be between two different values. If you add all this up, right, and if you take into account that the minimum would be, it never has to do this, right? The first time is the maximum value. It never has to do this one. That's going to be 4 times n minus 1, right? And then it's going to be between that and 6 times n minus 1 times for just that loop. Okay? If you add everything up, all of this up, and you add all the parts, you add 2 operations plus 1 operation for the other one oh no, here we go, hang on. If you add the 1 plus the 2 plus the 1 for this one plus this guy plus this guy plus this guy, and make sure you do the minimum and maximum, here's what you end up getting. Okay? You get this algorithm goes through either at a minimum 5n times n amount of operations, and at maximum it can go 7n minus 2. And if you do the math, it works out to be 7n minus 2 number of operations. OK, that was a lot of work. Again, that was a lot of work to just kind of break down this tiny little function, right? But now you can see that for primitive operations, that's what's going on. Everybody with me there? OK. In other words, we have a couple situations here. We've got a best case situation if the first value in your array happened to be the maximum of the whole array. That's the best case situation. It probably won't happen very often, but it could. And then you've got a worst case situation if the last element was the maximum. Okay, and that's the best case and worst case. Those are the two cases that we're going to be concerned mostly about when we're doing this kind of algorithm analysis, the best case and the worst case. Okay? We could think about the average case. Okay, and you could say, all right, let's see. In the average case, in this case, you're going to have, let's see, it's going to be halfway through. And you could do a little bit of math to figure that out. In fact, sometimes it ends up being a lot of math, right, to figure out what the average case is. In general, at least for this class, let other people worry about figuring out the average case. Right? We're not going to worry so much about the average case for these sort of algorithms, because we really care about the worst case. Right? In most things. When we get to some sorting algorithms, we're going to talk about how the worst case for one of the better sorting algorithms is actually pretty terrible, but the average case really is good. So other people have figured that out, and that's why we use that sorting algorithm most of the time. Okay? Best case, worst case. Questions so far on this? How we get there? OK. All right. So here's the summary. Okay? First of all, do we need this much detail? We certainly don't need the detail. We've decided, anyway, that we don't need the detail of like the machine level detail, right? Because there's lots of problems with that. There's lots of like pitfalls you can get with the machine level kind of analysis. Not to mention it makes your eyes bleed, right? So that's a tougher one. Do we even need this level of approach? We kind of do, in the sense that we need to kind of know where our bounds are, right? But as it turns out, we can even simplify this more. Okay? All we really want is actually a much bigger picture, like as they say, like the 50,000-foot view of what's going on. Okay? Sometimes it can trip you up, but we'll get to that kind of caveat in a little bit, right? But in the sense of array max, in the sense that we just looked at, all we really need to know is that as we add more elements to the array max, on and I shouldn't use on average, as we add more, the time that it takes to do that algorithm grows proportionately with n. Okay? In other words, you add another value, you add 100 more values, it's going to take n more, that's going to take that much more time because it's proportional to the number of values. If you add 100 times more values, I should say, then it's going to be 100 times slower in the worst case. Why? Because the n, right up here, this 7n is what wins out in this battle. Right? Do we care about the 7 and the 2? As it turns out, we aren't actually going to care about those, except in very certain circumstances where these numbers are so big, like the constants are so big that it will make a difference. And those are like special cases that you need to worry about, but not too bad. OK. Again, we're trying to make sure that we know that in this case, the speed of array max depends grows proportionally to the number of elements in there. Whew. OK. Now, you ready for this? We've got this idea that we're going to call big O notation. Okay? You can think of the O as standing for like on the order of. Okay? It actually has more mathematical meaning, and you can dig really deeply into this. If you guys end up taking algorithms class, you will dig a lot deeper than we're actually going to go. Okay? But we're going to come up with this mathematical construct called big O notation. Now, again, this is the next slide where, I think it's the next slide, where you want to cover your eyes if you're not like the mathematically savvy bunch. OK. Ah, boy. All right. This is what big O notation really is. OK. You mathematical types, write this down, go study it, be happy, do it. The rest of you guys do not need to worry about this part of the definition. I'm putting it up here to appease those who might say, hey, I want a little more detail. This is what's going on here. You've got a couple functions. Okay? You've got a couple functions, and you're trying to compare those two functions. One of the functions, at some point along its path, in this case f of n, at some point along this path, it will become less than this other function for the rest of time. Okay? Do you see how that works in this diagram? You've got two functions. F of n is this one. And at some point, in fact, that point happens to be n naught, or n0, right? It becomes less than the other one for the rest of time. Okay? The reason we have to define it that way is because some algorithms, as it turns out, even though asymptotically over time, they grow, they end up kind of following this one path. Before you get to a certain point, another algorithm that would be greater than it later is actually smaller. So you have to kind of define it this way. And all we're saying, and again, all we're saying is find some point where the one function, where that function is forevermore less than the other function. OK? All right. That's it for the mathy, like horrible mathy stuff for those who don't like it. And those you do, great. OK? You don't have to write this down. OK? If we're going to do our big O analysis, the dirty little trick here is for constants, and not constants that are like ginormous, like 10 to the 100 and all that, but for constants in general, you are going to actually just ignore them. Okay? And you're going to ignore factors in this function that you come up with that are going to, over time, be smaller in general than some other parts of the function. So for instance, in this 7n minus 2, right? The 7n minus 2, we figured this out. We went through and we said, OK, look, we counted everybody up. And we said it's going to be, for the array max, it's going to be 7n minus 2. Well, the 2 part, remember where the 2 part came from? Well, there's a couple different places. But we've got a couple little extras in there. When we're doing this algorithm, we've got to return from the function. We've got to set the initial maximum to the first value in the array. We have to dereference that array at the beginning. Then we have to set our loop constant, or our loop index once at the beginning. Those little one-offs are not going to matter. Okay? It's not going to matter to the overall runtime of that. Why? Because it's a constant factor. It happens every single time for all of them, but it's such a small amount of time compared to the overall picture that you end up ignoring it. So the 2 in this 7 minus 2 is gone. OK. Here's one that some people get a little upset with. The 7 is actually also going to be gone. It's a constant. And is it going to be true that if we go and say that as the array gets bigger, right, if you add 100 more elements, it's going to be 100 times bigger? Is that strictly true? Or is it going to take 100 times longer? What's really going to happen here? Okay, it's going to take how many times longer? 100 times, it's going to take 700 times minus 2 times longer, right? 698 times longer, right? That really is on the order of 100 times longer. Okay? We are not going to worry about those constants, okay? Because in the big picture, they don't make a difference to a graph that we could draw of this. Okay? It would shift the graph up and down a little bit, but it would not change the slope of it in that sense. Or it might change the slope, but it's not going to change it significantly enough to not make it comparable to other algorithms that we talked about. Okay. So if you do this calculation and you see that you've got 7n minus 2, we're just going to say that is order n. Okay, what does that actually mean? Well, we have a number of these that we're going to be talking about over the course of the semester. Okay? We've got constant time, we've got logarithmic time, we've got linear time, we've got quadratic time, we've got more than quadratic, which behaves in the same sense as quadratic, like cubic or whatever the next one would be. Right? A polynomial time, we call it. And then you've got this exponential time, which I mentioned before, not such a good thing because it takes lots and lots of time. There's a couple in here I want to put. There's also log time. Ugh. Where would log time fit in here? In the sense that we're going from the fastest algorithms to the slowest algorithms here. Okay? If you have to multiply n times the log of n, where's it going to fit into this schedule? Is it going to be faster or slower than log n? It's going to be slower. Is it going to be faster or slower than n? That's a trickier one. But it is going to be slower. Yeah, it would fit in here, right? It would fit in here. We're not going to see too many of those parts in here, okay? We're going to see some. We're not going to see too many. Constant time. Constant time is like the holy grail of computing, right? That means that if you have an algorithm that does not depend on the number of elements in it, you do something in that algorithm that does not depend on the number of elements in there, well, then you can say that it takes constant time to do it. In other words, it takes one go through the function and you're done. No looping, no extra operations based on the number of n. You just don't even worry. So it's when we find operations that are order 1 or constant operations, we love it. Okay? We have seen some of those in this class before. When you are putting elements into an array, does it take much time to go put that element into the array at a particular location? Do you have to loop through things to know where that location is? You do not, right? You've got an array, and if you have the index to that array, you can go right to that index location. You can put a value in there, and you don't need to walk through the array. You don't need to know anything else about the array, and you're done. That's called constant time. Okay? Inserting into an array is constant time. Unfortunately, you have to worry about things like expanding the array and all that. But that's like dirty little details that we're not going to worry about in this kind of analysis, especially for this class, right? Other ones are not such a good, like linear time is not bad actually, but we've seen structures where linear time it's very apparent that we have linear run times. What was a good example of that one? What was the other list that we used that it took on the order of n number of times to do something with? Remember? Current max, that was one we just did. Current max was one. How about, linked lists. Yeah, that's a great one. If you want to insert something into the end of a linked list, if you're not keeping a tail pointer, how do you get to the end? You walk through every single piece in every single part, and you have to follow link, follow link, follow link, right? Searching through a linked list takes on a linear amount of time. We'll see a little bit later, searching through an array can take a linear amount of time depending on how you do it as well. Okay? We'll get into quadratic in a minute and polynomial. Exponential is an interesting one too. I will come back to exponential one, but let me demonstrate exponential one. Okay, exponential one for you. Okay, anybody ever played a little ancient game called the Towers of Hanoi. You'll see it when I pull it up. You'll see if you've ever played it before. I'm just trying to see why I can't do this. Here we go. Oh, Let's see if I can get this on here. There we go. So I hope the screen comes up. This is what Towers of Hanoi. Oh, no, it doesn't. This is what Towers of Hanoi looks like. Okay. It's this little game where you've got 3 disks, or you've got 3 posts. You've got a whole number of disks on here, and you're trying to move the disks as a whole from one side, from one disk to like the third one over, and you can only move one at a time. Raise your hand if you've seen this one before. Okay, most people have. Don't raise your hand if you haven't, but if you haven't, I'll show you exactly what happens here. If you have 3 disks, okay, and you want to move this pile over to here, right? You can only move one disk at a time, and you can't have a disk that's bigger be sitting on top of one that's smaller. Okay? So how do you do this? You grab this disk and you like move it here, right? Actually, that's probably not the right way to do it, is it? Not a very good method. How about there? Because we're gonna have a little bit of a problem. I'm doing too many steps, as it turns out. And then I can only move that, and then I can move this one here, and then oh boy, I've definitely messed this up. But you can do it in fewer steps because you want to get to the end. All right. But anyway, and then this one goes here, and then this one comes over to here, and it'll probably tell me I did a bad job. All right. And this one can go over here now, and is that the biggest one? Yeah. I can't tell from this angle. I could look on my screen. OK. Anyway, and then this one goes here, and then this one can go over here, and then whoops, finally, this one can go over here, and hopefully it'll tell me I did 1. OK, I only needed 7 moves. I actually used 11 because I was terrible at these games. I used to hate this. Like when friends might have this, and I hate it. I've tried it. OK, as it turns out, OK, you can, and the nice thing about this program here is you can do up to 8 different disks, right? And if you start going up, it gets much more complex as you go along. It's not, even though I screwed it, I was also the one that lost it, like tic-tac-toe. All right. So anyway, it's much more complex now, right? Because now you've only got 2 spots to store stuff, right? And so I tried this method before, right? Now it's actually good. Those of you who know what we're doing. So did I do it wrong again? Oh man, hold on. Sorry, this one was here. I don't remember. Well, anyway, here, watch. I'm going to let it solve it for me. Okay, actually, I'm going to start over because I already cheated, or I already goofed, right? If we do 4 and then let the computer, I was better at like programming the algorithm to this. Doing it in my head is not so good. Okay, watch. Okay, it's going to do it like this, and it's going to put these on there, and then okay, so that's okay. I was so far so good, and then there, and then there, yeah. All right. And then notice it's taking a lot more steps, right? This is not quite as simple as the little 3 one that I did, right? You got to go back and forth and back and forth and back and forth because you have to add these guys up. You only got 2 spots to put things on, and there's that problem with it, right? Okay. So let's see. How many took 15 to get there? All right. So let's say we had 5, and I'm going to speed this up. Okay. No, I'm not going to speed it up yet. It does take a while to drop these guys on here. If you do 5, right, and then this, let's see, is it going to let me speed it up? Hang on. Ah, yes. Fast forward. Watch. Right? Okay. This is like really cool. But notice that it's still going, right? And that only took 31 operations. So the first one took 7 that I screwed up on. The second one took 16. And the third one took 31. Any idea of what that kind of pattern kind of looks like? I'll give it to you a different way. Looks like the bits we were talking about, right? It looks like kind of 2 to the n minus 1, right? Well, that's what this algorithm is. Okay, as it turns out, the best you can do. This is why if you want to do 8. Well, it's funny. I think on my computer back in my office, it's actually doing 8 right now. I think I'm like, oh, let's see what happens. Boop, and I did it right. It will solve it for you, right? And I'm not going to let it go, but it'll take some time. If it took 1 second to do this, to do 1, right? Then it would take 2 seconds to do 2, and 4 seconds to do 3, and 8 seconds to do, et cetera, et cetera. Let me fast forward this one. still won't go quite as fast as it needs to. This will go on for a while, right? Why is it going to go on for so long? Because you've got 2 to the 8th, which is 128 times as many, sorry, 2 to the 100, it's 128, what steps is it going to be? No, it's going to be even more than that. Yeah, 255, is that what it's going to be? Yeah, all right. So anyway, this is why this frustrated me. I can never pay attention that long. And even if I knew the algorithm, I'd forget it. Anyway, so OK. So you get the idea. There are certain algorithms that, by their definition, they end up taking that amount of time. OK, let's see. Keep going, keep going. That's right. I set my computer to do it. There we go. 255 amount of time. 255 steps. OK, which, if you tried to do 9, right, it would take, what, 511 steps and so on, right? It is an exponential growth and not the most pleasant thing to have to deal with in an algorithm. OK, you don't want algorithms that take exponential amounts of time. OK, all right, because they're so slow. OK, so let's see. The dirty little trick that we said before. Cut out all the constants and cut out any factors that are not as big as the biggest factor. So if I gave you the following, this is some wacky algorithm, and we ended up calculating some steps here and saying, OK, look, it's going to take 20 n cubed plus 10n log n plus 5. Get rid of everything that's smaller than n cubed. Whoop, just gone, right? This is n log n. It's going to be smaller than n cubed, and 5, of course, is a constant so smaller. So, and then take all the constants. They're gone too. So if you look at this function, this actually is order n cubed. Why? Because you can get rid of all those things. So it's not quite as bad as you think. OK? And any polynomial is going to be bigger than any other polynomial that's smaller than it. Questions on that? OK. Let's take a look at a couple loops here. OK? Loops are another one that are interesting. OK? If you look at this loop, all I'm doing here is I'm not really even doing anything interesting here. I'm just saying there's a result. And every time through this loop, I do the loop twice, right? And then I get the result here. And then I add one to the result. And then at the end, I return the result. OK, that's all I'm doing for this loop. Okay? The inner loop has a complexity of what? We are not going to worry about this little part. We're not going to worry about the last little, or the adding 1 on the end each time through the loop. What we're worried about is how many times does this loop happen? Well, it happens on the order of n times. Sure, it might be n minus 1, but it happens on the order of n times. Okay? The outer loop here. Well, the outer loop goes also n times, but what happens? Okay, it also does n times, but on the inside you've got n times as well. So overall, the complexity of this one is a quadratic complexity. If you have loops that have 2 elements, and you're going through both for the entire course of the element, you will, for each of them, you will have a quadratic type of complexity. This is not a particularly good complexity. It gets pretty big pretty fast, right? So doing double loops like this, unfortunately, there are lots of times where doing double loops you can't get away from it, right? There's a really good example in the graphics on your computer, right? To go through the pixels on your screen, right? You need to go all the way across, and you need to go all the way down if you want to get every pixel on the screen, right? Well, that's if your screen happened to be square. Most aren't, but if you happen to be square, you'd have to do n times across and n times down, which is a quadratic function. This is why graphics processing units, or GPUs, are so important today. Because they've taken this problem, they've said, how are we going to break this up, and how are we going to make it so that going through this n squared complexity algorithm is going to be fast enough so that people can get to play their cool games, right? Or do the graphics they want to do. Well, they've ended up saying, we've got to parallelize the problem. We've got to use lots of processors to do each individual pixel and blah, blah, blah. So lots of people are thinking about this because of the problem with n squared complexity. OK, it's kind of important. If you looked at a 3-loop one, right, same idea. Inner loop is n, next loop is n, next loop is n. That is an n cubed or a cubic complexity. You really want to avoid this. 3-dimensional graphics. Oh, don't get me started, right? because you have to 3 dimensions, right? You have got to go through these loops like this, and it's painful, right? It's painful because they get big really fast. Okay? I've actually got some examples of this. Let's see, whoops. I've got some examples of this here. And this, I forgot to do the Unix tip of the day. If you do the time, right? This is if we time a function. This is the array max one that we've got, right? If you type time and then what you are doing, okay, like in other words, not Tim. If you were doing time and then the actual function that you're calling, the computer will tell you how much time it took. We did talk about this earlier. I forgot, way back in like the first day or second day, right? We talked about how much time these things take. Okay, this one took 0.629 seconds. If I did 10 times fewer, it takes roughly, let's see, 10 times less time, right? Because this is a linear algorithm. The problem with doing this on a computer like this is it's hard to get things to go. Some linear algorithms, it's hard to make them slow because your computers are so darn fast, and making numbers big enough that fit in regular variables is not always the easiest thing to do. I guess with long integers you could do it. But so that's the array one. Let's see. I also have the asymptotic analysis nested one, which is our quadratic nesting. And if I do this, it's interesting. If you do this one, so let's start out with 1,000 for my quadratic one, right? Whoops, let's time it. Time like that. OK. If I time it, OK, it takes 0.005 seconds. That's not much time, right? That's like a tiny little amount of time. If I did 10,000, well, you'd hope it would be like a quadratic factor, right? Well, that one's actually not too bad. It actually does. Oh, I forgot. I was going to say it was going to be like 0.005. I had to cheat a little, and I actually had to add extra like stuff in the loop to make it slower so that it's actually worked. So when you look at the code later, you'll go, what's this little statement? That's not even doing anything. You'll go, oh, it's because Chris had to cheat because his computer's too fast, right? Thank you, Apple, I guess, or Intel. OK. Well, anyway, so in this case, you've got, so if something takes 0.05 seconds for 10,000 or for 1,000 and takes 0.192 seconds for 10,000, let's see what would happen if we did 100,000. Right? It's actually cranking away right now, doing my fake little like thing here, right? It's going to take how much more time? If we do 10 times the amount, it should take 100 times more time, right? So 100 times 0.192 seconds should be roughly what? 19 seconds? Took about 18.4 seconds, almost 19 seconds, right? So the quadratic equation, or the quadratic operation, or quadratic functions take the quadratic amount of time more, the squared amount of time more. We could do let's see, this one's this one is, I don't know if I changed this one. I might not have. Oh, no, I did. This one's the cubic one, right? And if I did this one, if I did 10,000 for this one, it's going to take what? Cube times, so 10 times more, it's going to take let's see, it's going to take 1,000 times more time. I'm not going to sit around and wait for 1,800 seconds, right? Just not going to do it. Half an hour or whatever. Not worth the time to do that, OK? Although maybe this one, I think this one I have my computer back at the office doing the same thing, cranking away. Increasing the entropy of the universe, as they say. OK, so those are the quadratic and the cubic types of functions. By the way, have we seen this anywhere in the code we've seen so far? You seen a cubic one? Do you remember? Any code that we've had for homework assignments? Yeah. Yeah, that little, what I called the advanced test, which turned out to be not quite as advanced as it probably should have been, was exactly this. It was a looping through 3 different breakfast, lunch, dinner, right, operations, where it had to permute all of the operations. And so that's how you actually do permutation. Well, not quite. That's a little more subtle than that. That's how you do combinations. But yeah, you want to get through all of them. That's how you'd have to do it for 3 variables, 3 loops. OK? All right. Cubic complexity for this one. OK. Let's now look at a little bit more code. Let's look at searching. So we talked about searching way back at the beginning of the class, and we've kind of gone through some of this before. It seems like a lot of code. Again, this is C++, making my job hard, right? To do this like searching, you have to do a whole bunch of like boilerplate stuff, which is kind of annoying. But here's what I'm doing. I am searching through an array. I'm passing in a parameter of the array. I'm passing in the length of the array. And I'm passing in some number I want to find. Okay? Well, in this case, all it's doing is it's got this loop, and it's going through the loop, and it's saying, if the array equals a number I want to find, the answer is true, and so we're done. Like, in other words, go through this array. Check to see if the next number is the number that we are looking for, and return it. The reason I can do the following is say, if the array is greater than or equal to the number I want to find, right? I'm done, is because this is actually, I'm only allowing sorted arrays here. Okay, so if you're going through a sorted array and you get to a point where the number you're looking for is greater than is greater than the number that you are up to, no, less than. The other way around. If the number in the array is, let's see, the next number in the array is, help me out here, less than the number that you're searching for, it ends up being, you can stop because you know you've gone too far, right? Greater than, I did mess it up. Point is that we can go through this, and this is a linear algorithm. Why is it linear? You've got a loop here that's going through, and every time it checks. What's the best case here, though? If you've got a sorted array and you're doing it linearly, right? Or, yeah, if you're doing it linearly and the array and what you're searching for is in the array, how long does it take? Well, that's not, I guess I didn't phrase it right. If the first element in your array is the one you're looking for, how long does it take to do this algorithm? Like one operation, right? One time through the loop and you're done. Okay, so the best case in this case is instant, like, right? You can come back and you can get the answer instantly. What's the worst case? As if, in other words, your element doesn't actually exist, like when it's too big it's bigger than all the other elements in the array. N times, right? So we're going to, when we do the when we do the complexity analysis, we're going to say this is on the order of n. It's linear. Why? Because the worst case is as bad as it gets. And the worst case in this case, you have to go through this loop every time, get to the end, and say, oh, my value wasn't there. Okay, and it was too big. Okay, that's how we're going to do the analysis for this one. We can do a different type of search. We've talked about this before. Okay, we can do a search called a binary search. We have mentioned it in class before, and it's actually fairly straightforward, right? Well, it doesn't look like it up here. But what we're going to do is we're going to go through the array, same array. We're going to go through the array, and we're going to check and see if our value is the one that we want, if we found it. And then it's going to split the array in half. And then it's going to only check the half that's either lower or of the values that are lower or the values that are higher than the one that we are looking for. And then when it finds out which part, if it checks the next value, it's going to do the exact same thing, and it's going to cut it in half and cut it in half and cut it in half. This idea of cutting your problem in half leads to what kind of complexity? Logarithmic complexity. If you can cut your problem in half at every step of the way, you will end up with logarithmic complexity. Okay, halving it each time, and you can end up doing that. I have another one here which shows you that one. Let's see. Search. I'm going to time asymptotic search. Search. Hang on. I spelled it wrong. Oh, analysis. Asymptotic analysis, search 1. What I've got is, and let's see, I forget how I did this. I think I put in the amount and then another, hang on. I forget if that's what hang on, let me check this again. I forget exactly how I did it. 10, 1. Nope. It's going to search for the first parameter here. It's going to search for 10 in a really big list. Okay? It's going to search for the 10 in a really big list, and it actually takes some time to create that list to begin with. That's why it actually takes some time. But if I have 11, if I search for 10, right, it's going to take 11 comparisons. It's going to go through this list, which happens to be the numbers in order, kind of like what we did on the first day of class. And it's going to search through that linearly, and it's going to take, in this case, 5 seconds. If I did 100, well, that's probably not a good idea, because it will take a lot of time. But Oh, actually, that's not, no, I lied. It didn't take a lot of time. Here's why. Creating the array is some initial overhead. That's the constant that we're talking about. Like creating that array takes almost 5 seconds, actually. In fact, this actually took less time, as it turns out, probably because it had cached some of these values. But let's do 1,000 and see if we can actually make it get up above 5 seconds for this thing. Nope. It's going to take less time even. All right. Let's see. Let's try it again with 10,000. So eventually, it should start increasing such that we can check it. Yeah, all right. That's 5.2. And then if we want to search for 100,000, it doesn't actually take that long to do a search through 100,000 elements that they're already in. So we would have to get up significantly more. There we go. So 7 seconds when you're doing 10,000. What you have to do is you basically have to subtract out that initial 5 seconds, and then that's the time you're going to think about. But the point is that for the search, for the linear search, right, then what you have to do is you have to go all the way through, and it takes on the order of the number of elements. Okay, so this one, let's see, 5 seconds. It took about 2 more seconds than the previous time, so maybe 9 or 10 seconds it should do this time, right? No, 2 times 2. Yeah, it should take. Well, I'm not sure exactly how long it's going to take. We'll give it another few seconds, but it should take on order of 10 times longer than it did before. There we go, 26 seconds in this time. Why? Because it took about 2 seconds before. Now it's going to take about 10 times as much this time. Okay, for the linear search. The binary search, on the other hand, okay, if we do the binary search, the nice thing about the binary search is, well, let's see, 2. If we search for this, it takes, not even there, hold on. Asymptotic analysis, search binary. There we go, and we're going to time it. There we go. Okay, so this one takes some amount of time. And what it's doing is it's actually printing out all the comparisons that it needs to do. So it actually compares with 0 and 999,000. It says, am I the value there? Which one's it greater than? It happens to be less than 999,000. So it goes halfway, and then halfway, and then halfway, and halfway, and halfway, right? And well, halfway to here. And then it knows it's bigger, so it goes halfway back the other direction, et cetera. And it finally does all those comparisons and then finally finds it. This one took about 4.84 seconds. If I do 10 times more, well, it should also take about 4.7 seconds. Because on the order of the number of elements, we have added twice the number of elements, but we are 10 times the number of elements that we're searching through. But it's a logarithmic search, and so you don't have to actually worry about the n is, it's log n, which we barely even changed the amount of the log n part of it. Okay? All right. Just a couple quick numbers before you go. If we have an algorithm that has 1,000 elements, and it takes 10 nanoseconds to do the logarithmic one, the constant time would take 1 nanosecond. The linear time would take 1 microsecond, which is what? That's 1,000 times bigger than 10 nanoseconds. Sorry, 1 microsecond is 100 times bigger than 10 nanoseconds. Quadratic is a millisecond, and polynomial would take a whole second if the 10 nanoseconds is such a short amount of time. Anyone guess on how long the exponential solution would take? It's like 10 to the 284 years. Okay, we're not talking like a year or whatever. We're talking like this is really bad. Okay? It's like the heat death of the universe. Okay, like way past that. Okay? And if we were to, now those numbers, by the way, those numbers looked pretty small altogether. I mean, look, if you have a quadratic, a millisecond, that's no time, right? A second, that's not too bad. I can wait for a second, right? Well, I guess it would be cubic, not polynomial in that case. Cubic would take a second. If we bump it up and now it takes 10 milliseconds to do the log n version, it takes a second to do linear, it takes 17 minutes to do the quadratic, 694 hours to do polynomial, and the heat death of the universe again, I mean, doesn't matter at that point. Okay, so, oops, last slide here. All right, last slide. If you want to figure these out, constant is not dependent on n. Linear, reduce the problem by a constant amount each time you go through a loop. Logarithmic, half, a third, etc. Quadratic, doubly nested things. Cubic, triply nested. Exponential, reduce a problem into 2 or more subproblems. 2 or more subproblems of a smaller size. So all of a sudden, you're kind of going the wrong, you're making smaller problems, but you're making many more of them, and that's the problem with that. Okay? All right. I'll see you guys Monday.